Suppose f of x equals x squared on the closed interval between 0 and 1. Let P be a regular partition of the closed interval from 0 to 1 into n subintervals. We need to first find delta x and write xi in terms of I and n. So if we just draw the interval, it probably will be a lot easier to explain. F of x equals x squared, a very simple function to draw. We can zoom in quite a lot because we're only interested in the interval between 0 and 1. So we know that 0 squared is 0 and 1 squared is 1. So we'll put the 1 up there. Just going to go through that. And we know that x squared, when it's positive, it just goes up like this. Something like that. It'll just keep rising, so we'll chop it off there because we're not interested in anything else. That's the bit of the function that we care about. We are talking about an area, and we're talking about a partition, so it certainly ends here and it starts here, and then it says we split it up into n subintervals. So we're basically making strips like this, and they are equal. They're regular. It's a regular partition, which means all widths are equal. So something like that. So obviously we're going to have a lot more strips than this. The principle of Riemann sums is that you use limits and you let n approach infinity, n being the number of strips. So the number of subintervals approaches infinity, which means the width of the strips approaches 0. That's what we do. But I'm just going to show you with a few strips just so you get the principle of what's going on. So this is x0, which is 0. It's the value at the beginning of the interval. The second one you will call x1. This is x2, x3, x4, x5, and the last one you would call xn. Right? So for any given strip, what I mean is, say, if I pick the third strip, so 1, 2, 3, if I pick this one here, that would be the third strip. So we know that I equals 3, right, for the third strip. When I say strip, really I'm talking about a rectangle. I haven't actually drawn the rectangles yet because we need to think about what the height is. But you know, when I equals 3, you have xi, which in this case is going to be x3, and you have xi minus 1 would be x2. So what I mean by that is, for any given strip with this I, remember I is just a counter, so when I is 3, you have two choices for xi, e.g. this one here or this one here, such that f of xi gives a height. So if we used I minus 1, we would be using this height, e.g. that would be f x2. So if we used it for this strip, we would be clearly be getting an underestimate of the actual area of that strip. If we used f of x2 for the second strip, then we would be using an overestimate. And in the same way, if we used f of x3 for the third strip, which is here, so if I can fit that, that's f of x3, then we will be getting an overestimate because we just used the area of the rectangles. So back to the actual question, what is delta x? Now you know delta x, which means the width of each strip, and if it's a regular partition they're all the same. So delta x is that, and it's defined as b minus a over n. So b minus a is the width of the whole interval. In this case it's 1 because it's 1 minus 0. This is 1 and this is 0. And n is the number of strips. So in our case it's 1 minus 0 over n. 1 minus 0 is 1. So delta x for this is 1 over n. For the little partition I've drawn, obviously there's not many at all, and I could actually put a definite number in, but for an actual Riemann sum where we're going to use limits, 1 over n is the general width of each strip when there's n strips, and we're going on an interval from 0 to 1. We also need to find xi in terms of I and n, right? So xi equals x0 plus I delta x. Just think of this as it's like an arithmetic sequence really. Remember, I is a counter. I will be 1 for the first strip, 2 for the second strip, 3 for the third strip, all the way up to n. So if I is 1, right, so xi will be x1 because it will be x0 plus 1 of these delta x's. Remember, delta x is just this distance here, so we just jump delta x and that will get us to x1. If I is 2, well, it will be x0 plus 1, 2 delta x's, so that will get us to x2. So xi is x0 plus I delta x, but we've been asked to write it in terms of I and n, so we're going to use this 1 over n. It equals x0, which we know is 0 for this particular one because of the closed interval between 0 and 1. That's where we're looking at the function. So it's 0 plus I times 1 over n. 1 over n is our delta x. So that just becomes, well, 0 can disappear. I times 1 over n is I over n. So xi equals I over n. Not to be confused with xi minus 1, which we will deal with very soon. Part B, show that the lower Riemann sum is given by ln equals 1/3 minus 1 over 2n plus 1 over 6n squared. So now this is quite complicated. And it's a bit unfortunate that they've asked us about the lower Riemann sum first because it's a lot easier to calculate the upper Riemann sum in this case. It does depend on the function. But for the lower Riemann sum, well, we are going to, if I take you back to this diagram, for the lower Riemann sum, we need to pick the values of xi for each interval such that it gives the lowest height. The width is always going to be the same. Remember, the Riemann sum is, well, it's the sum from I equals 1 to n of all the fxi times delta x. fxi times delta x, right? So what all that means is fxi is the height of the rectangle, delta x is the width of each rectangle. This just means add them all up, right? And for a regular partition, well, delta x is equal for each strip. So I suppose technically I could have had a delta xi in there, but because it's the same for every one, then I'm just going to write delta x. So if it's the same, you can just pull it out, equals delta x times the sum from I equals 1 to n of all of the fxi's. Now that's a general Riemann sum. Now remember, we can pick any xi within an interval, and we're going to pick for a lower Riemann sum, we're going to pick whichever xi makes this fxi as low as possible. So if you look at this, it's always going to be, so for the first strip, when I is 1, clearly if we pick x0, that's going to give us a much smaller area. Actually, it gives us no area in this case than if we pick x1. If we're on the second strip, if we pick x1 as our height, it's clearly going to give us an underestimate. So what we need to do, we don't want xi, we want xi minus 1. Right? So for the lower sum is written like this. It's going to be delta x times the sum from I equals 1 to n of f of x I minus 1, right? So xi minus 1, if you think, well, xi was x0 plus I delta x. So xi minus 1, well, we're going to have to add 1 less each time. So if you think when I is 1, I want to be using x0, so I'm going to have to add on no delta x's. So it's going to be I minus 1 delta x's. When I is 3, I want to be working with x2, so I want to add on 2 delta x's from x0. So xi minus 1 equals x0 plus I minus 1 delta x. So that's a general result. Now we can make it specific to our actual problem. So in our case, well, x0 was 0 plus I minus 1 times delta x, which we said was 1 over n. Okay, so that becomes, well, 0 disappears, it becomes I minus 1 over n equals I minus 1 over n. So that is our x I minus 1. So if we want f of xi minus 1, remember what the original function is, it's just x squared. So it's you take your I minus 1 over n and you square it, or you take your xi minus 1 and you square it. So that means f xi minus 1 equals I minus 1 over n, and then you square it, right? So we're good so far. So putting it all together, the lower sum equals delta x, which is 1 over n, times the sum from I equals 1 to n of f of x I minus 1, which is I minus 1 over n squared, right? So we can simplify this a bit just by thinking, well, I minus 1 squared over n squared equals 1 over n times the sum of from I equals 1 to I equals n of I minus 1 squared over n squared. And now we can do even more because we're dealing with an I counter. So this counts i's, it takes an I value and it takes one away and squares it, and then it just divides by n squared. The n is not going to change, n is just n. So this is, you could regard this n squared as a constant, so I'm going to pull that out. I'm going to pull it into here, so it's going to be 1 over n squared times 1 over n, which is 1 over n cubed. 1 over n cubed times the sum from I equals 1 to n of I minus 1 squared. Right, so now this is the tricky bit. You need to know this very important result that's going to help us a lot. So a very important formula that you probably don't think you've seen before. You will have done, because when we did proof by induction, it's one of the most common proof by induction examples. I've done it as a works example. The sum of the first n numbers. The sum from I equals 1 to n of I squared, so as in the sum of the first n square numbers, equals n times n plus 1 times 2n plus 1 over 6. Now, I'm not sure entirely if you need to remember this or not. I would like to think you'd be given it, but I can't guarantee it. So it's useful. This is the main exact application I've seen it be useful for, to be honest, but certainly without this fact, I don't know how you're going to make much progress with this Riemann sum question. And so we're going to use this. We have almost that. We have the sum from I equals 1 to n of I minus 1 squared. We don't quite have this, so what we can do is just think about what this means. Now this means you take one less than I and you square it. So if we were to write this series out, it would be well, if I was 1, it would be 0 squared. If I was 2, it would be 1 squared. So this would be 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared. So what we can do, we can just rewrite this a bit into, we can now say 1 over n cubed times the sum from I equals 1 to n of I minus 1 squared. Well, it's the same as if we just started at 0 and went to n minus 1 equals, keep the 1 over n cubed times the sum from I equals 0. If we just start at 0 instead and go to n minus 1, and then we can just write I squared in here, which means that we can apply this formula. Okay, so now, using this result, we can just plug in the values, except at the top, instead of an n, we have an n minus 1. So we're just going to have to write wherever there was an n before, we just have to replace it with an n minus 1, and you may need to use a bracket. So this now becomes, well, it's 1 over n cubed, that hasn't moved, times, well, it's going to be, well, it's n, which is n minus 1, definitely need a bracket there, times n plus 1, which is n minus 1 plus 1, which is just n, times 2n plus 1. So that would be 2 n minus 1, n minus 1 plus 1. So we'll tidy that up a bit. Plus 1 plus 1. And then don't forget it's all of that over 6. So now we've got something we can work, and we can show that it equals what it's supposed to. Equals 1 over n cubed times, I'm not going to do a lot with the over 6, but this is, I'm just going to expand this bracket first, so that's going to be n squared minus n, times, well, in here you've got 2n minus 2 plus 1, so that's 2n minus 1. Don't try and do too much of this in one go. If you make a little mistake here, you're ruined, and it really wasn't worth it. There's so much going on, there's so much hard stuff that the chance of making a mistake just because of a bit of cognitive overload is really high here, so just take that extra line. Okay, so now I'll expand this bracket. This is going to be equals 1 over n cubed. In fact, I might just pull this 6 out now. 1 over 6n cubed times n squared times 2n is 2n cubed, and then I've got n squared times minus 1, that's minus n squared, minus n times 2n is minus 2n squared, so that leaves me minus 3n squared. Just told you not to do all that in your head, but never mind. And then you've got minus n times minus 1, which is plus n. And now we just need to bring this in here. So now we have 1 over 6n cubed times 2n cubed, or 2 over 6 is 1 over 3, and n cubed over n cubed is just 1. So this first term is 1/3. And the second term, well, 3 over 6 is 1/2, n squared over n cubed is 1 over n. So it's negative, minus 1 over 2n plus 1, well, it's 1 over 6, which is 1 over 6, n over n squared, oh sorry, n over n cubed is 1 over n squared, so 1 over 6 n squared, and that is the lower Riemann sum. So part C, show that the upper Riemann sum is given by un equals 1/3 plus 1 over 2n plus 1 over 6n squared. So the upper Riemann sum, un, is going to be delta x, and delta x, remember, was 1 over n, times the sum from I equals 1 to I equals n of, and it was f of xi. Now we had xi, we calculated it in part A, it was just I over n, so it's I over n. And f of xi must be that squared, right? So in the same way as in part B, we can simplify this, or we can expand this, get rid of the bracket, and then we can pull the n parts out, so it equals 1 over n, times the sum from I equals 1 to n of I squared over n squared. And remember, this is an I counter, so effectively n squared is just a constant, so we can just pull it out, or pull 1 over n squared out. So you're going to have equals 1 over n cubed times the sum from I equals 1 to n of I squared. Now this is a lot easier than the lower sum. We don't have to do any adjustment. Remember, I'll just write it on here again. So recall the sum from I equals 1 to n of I squared, as in the sum of the first n square numbers was n times n plus 1 times 2n plus 1 all over 6. And we can just put that straight in here. So now we have equals 1 over n cubed times n plus 1, 2n plus 1 all over 6. So in the same way as before, I'm going to pull the over 6 out. So that's going to equal 1 over 6n cubed times 2n cubed plus, well, you've got n squared plus 2n squared, so that's plus 3n squared plus n times 1 is n plus n. And then if we just now expand this bracket, un equals, so 1 over 6n cubed times 2n cubed is n cubed over n cubed is 1, 2 over 6 is 1 over 3, so it's 1/3. They're all going to be positive. Plus, then you've got 3 over 6 is 1 over 2, n squared over n cubed is 1 over n, so you've got 1 over 2n plus n over 6n cubed is 1 over 6n squared. Right, so now we have our expression for un, we have our expression for ln, and now we're ready to do the limiting bit, and we can start squeezing. Okay, so we know that the true area is somewhere between the upper area and the lower area, right? Area is clearly less than or equal to the upper sum for the upper rectangles, greater than or equal to the lower sum for the lower rectangles. So what you can do, you can now write some limits in, use the squeeze theorem. So the limit as n approaches infinity, as in the number of strips of the true area, which is just going to be the actual true area, is less than or equal to the lim as n approaches infinity of the upper bound of area for the upper rectangles, and it's greater than or equal to the lim as n approaches infinity of the lower bound. Right, so if we write these in, remember the lower bound for area was 1/3 minus 1 over 2n plus 1 over 6n squared, so we need the limit as n approaches infinity of all of that, which should be quite simple, and that is less than or equal to the lim as n approaches infinity of the true area, which is less than or equal to the lim as n approaches infinity of the upper bound, which we just calculated, which was 1/3 plus 1 over 2n plus 1 over 6n squared, right? You can clearly see very basic limits. So as n approaches infinity, 2n approaches infinity, 1 over 2n, this is going to approach 0. So is this term, and so is this term. So this is going to be 1/3 is less than or equal to the lim as n approaches infinity of the area, which is less than or equal to 1/3. Therefore, area under the curve y equals x squared between 0 and 1 that area, the true area, equals 1/3 units squared.